This video is for section 12.1, inference for linear regression. So before we begin, we talked about linear regression and how that was y equals, or y hat equals a plus bx. So we talked about that in Unit 3. And so now we're going to move on and talk about what can we do with that linear regression. So suppose we have n observations on an explanatory variable x and a response variable y. Our goal is to study or predict the behavior of y for given values of x. That's what we did in Unit 3. So there are certain conditions that have to be met in order for us to use regression. So first you got to check and make sure that it actually is linear. So the actual relationship between x and y is linear. For any fixed value of x, the mean response mu y falls on the population or true regression line. The mu y equals alpha plus beta x, basically a plus bx. The slope, beta, and the y-intercept alpha are usually unknown parameters. The second is independent, so individual observations are independent of each other, so one does not affect the other. Normal, for any fixed value of x, the response y varies according to a normal distribution. Equal variance, the standard deviation of y, call it sigma, is the same for all values of x. The common standard deviation sigma is usually an unknown parameter. And random, the data come from a well-designed random sample or randomized experiment. Now, you may have noticed that the first letters of all of these conditions spell out liner. So that might be a good way for you to remember what the conditions are for regression so that you can do regression inference. So if you check all of the conditions that make up the word liner, then you should be able to do regression inference. All right, so how do you check these conditions? So for linear, you would examine the scatter plot to check that the overall pattern is roughly linear. Look for curved patterns in the residual plot. Check to see that the residuals center on the residual equals 0 line at each x value in the residual plot. For independent, you would look at how the data were produced. Random sampling and random assignment help ensure the independence of individual observations. If sampling is done without replacement, remember to check that the population is at least 10 times as large as the sample, your 10% condition there. Normal, so with normal you would want to make a stem plot, a histogram, or a normal probability plot of the residuals and check for clear skewness or other major departures from normality that we've talked about when we were talking about what it means to be normal and that kind of thing. Equal variance means that you're going to look at the scatter of the residuals above and below the residual equals 0 line in the residual plot. The amount of scatter should be roughly the same from the smallest to the largest x value. And random, you're going to see if the data were produced by random sampling or randomized experiment. So let's look at an example of how you would check conditions for linear regression and inference that goes along with that. So Ms. Barrett's class did a variation of the helicopter experiment on page 738. Students randomly assigned 14 helicopters to each of the 5 drop heights: 152 centimeters, 203 centimeters, 254 centimeters, 307 centimeters, and 442 centimeters. Teams of students released the 70 helicopters in a predetermined random order and measured the flight times in seconds. The class used Minitab, which you guys saw last week, to carry out a least squares regression analysis for these data. A scatter plot, residual plot, histogram, and normal probability plot of the residuals are shown below. So this one would be your scatter plot. This one would be your residual plot. This one, of course, is your histogram, and this is your normal probability plot. If you look at this one, you may say, okay, how did you know which one was which? Frequency is always going to go with your histogram. Your z-score, of course, has to do with your normal probability plot. You've got your residuals here, and then this one is just your scatter plot. So to check whether the conditions for performing inference about the regression model are met, remember we said that the word that we were going to use to help us remember was linear. So that means first I need to check and see if it's linear. All right, so if I'm going to check and see if something's linear, I'm going to have to look at the scatter plot, which is the first graph. So if I'm looking at the scatter plot, we can see that it has a clear linear form. Actually, let me back up a second, and let's say that we're going to look at the scatter plot. So it has a clear linear form. For each drop height, so that's your x or your explanatory, for each drop height used in the experiment, the residuals are centered on the horizontal line. So if I'm looking at this is the horizontal line, residual equals 0, and I can see that everything's kind of centered on that horizontal line. The residual plot shows random scatter about the horizontal line, which is good and also means that it's linear. So from the residual plot, the residuals are centered on the residual equals 0 horizontal line. It also shows random scattering around that line, which is good. Remember we talked about how you wanted to have some random scattering because that lets you know that it was linear. If you were to see some sort of circular pattern, that would mean that we did not have, we could not use linear regression. Next, we would look at independent. So basically, when we are talking about whether something is independent, we would look back in the information about the problem and make sure that it was in a some sort of random assignment. We would also make sure that one helicopter was not going to affect another helicopter. So basically, we would say because helicopters were released in a random order. We know that because it was stated in the problem. And no helicopter was used twice. Knowing the result of one observation should give no additional information about another observation. All right, next in liner we have N for normal. So if we want to check that we have normality, we're going to look at the histogram. So when we look at the histogram, We can tell that the histogram of the residuals, which is what we have here, is single peaked, which just means it has one place where it peaks. We can also see that it's unimodal. And we can tell that it has some sort of a bell-shaped curve. Remember, if all of those things are true, then we do have normality. All right, next we have E. So E stands for equal variance. So when we are looking for equal variance, we're going to go back to the residual plot, which is this one. And we're going to check that it seems like everything is kind of equal on both sides of the residual equals 0 line. So this is the residual equals 0 line. We want to make sure basically that we have the same amount of scatter above and below that line for everything. So it looks like we have similar amount of scatter about residual equals 0 for 152, which would be this one, for 203, which would be this, for 254, which is this one, and for 442. We do seem to have more variance around 307 because we see that this is a little bit more spread out than it was down here. So we do have a little bit of variance that's kind of off there, and that's going to be important later on. So for equal variance, we would say residual plot, and you'll always look at the residual plot for the equal variance. So the residual plot shows a similar amount of scatter about the residual equals 0 line for the 152, the 203, 254, and 442 drop heights. We would say that there is more variance around the 307 drop height. And the last one we have to look at is R, which stands for random. So to check and see if it's random, we just have to make sure that it's stated in the problem that this was a random design or a random experiment. And so this one did say that it was random, so we're good on that. All right, so once you've checked all of your conditions, then you would basically just say whether or not you think that you can use a regression model and make inference from that regression model. So if all of these conditions are met and you don't seem to have any problems, then you would say that you feel comfortable or safe performing inference about the regression. What you would say for this one, because we did have just a little bit of an issue here with equal variance, you would say aside from slight concern about equal variance condition, and so the problem with that was the more variance around the 307 drop height, we should be safe performing inference about the regression. So even though it's not something that is going to prevent you from performing inference about the regression, it is important that you state that there is a little bit of concern so that if anything weird happens when you're doing the inference about the regression, then you can kind of blame it on this particular condition here. All right, so we are going to combine a little bit of the confidence interval stuff that we did a couple of units back with the stuff that we did in Unit 3. So what you're going to do is you're going to be calculating t-intervals for the slope of a least squares regression line. So when conditions for regression are met, like we did in the last example, a level C confidence interval for the slope, beta, or what we've been calling B, of the population or the true regression line is B plus or minus T star times SE sub B. In this formula, the standard error of the slope, which is the SE sub B, is equal to S over the standard deviation of S, or the standard deviation of X, times the square root of n minus 1, and the t star is the critical value of the t distribution with degrees of freedom equal to n minus 2, having an area C between negative t star and positive t star. So let's look at an example using the confidence interval for the slope. So earlier we used Minitab to perform a least squares regression analysis on the helicopter data for Ms. Barrett's class. Recall that the data came from dropping 70 paper helicopters from various heights and measuring the flight times. Some computer output from this regression is shown here. We checked conditions for performing inference earlier, so we know that we're good with that. And so for the first problem, we're going to identify the standard error of the slope, SE sub B, from the computer output and interpret this value in context. So basically, we want to know what is the standard error of the slope. So SE sub B is going to be your SE coefficient column of your output. So basically, it's going to be this number. And the reason that I'm going with that number is because in my regression line, my drop height would be the slope. And so I want to make sure that I'm using the standard error of the slope because it was SE sub B. So for that, you would just say that it's equal to 0.000218. And so then we want to interpret what that means. So basically, your standard error of your slope would mean if we repeated the random assignment many times, the slope of the sample regression line would typically vary about 0.0002 from the slope of the true regression line. All right, B says find the critical value for a 95% confidence interval for the slope of the true regression line. Then calculate the confidence interval. Show your work. All right, so for B, what you would need to do is you would say because conditions are met. That's what we did from the last example on the last page. We can calculate somehow my contraption here put an I in the word calculate. So we can calculate a t interval for the slope based on degrees of freedom equal to n minus 2. N, of course, is 70 because we had 70 helicopters we were looking at. So 70 minus 2, which gives us degrees of freedom equal to 68. All right, so what you're going to have to do is you're going to have to use Table B, which is in the packet of stuff that you got at the beginning of the year. It's on one of the tables, one of the laminated sheets that you got at the beginning of the year. It's also going to be provided to you on the AP exam. So it's Table B, which looks like this. And so you're looking for a t distribution of critical values. You're going to find the degrees of freedom at 68. All right, so your degrees of freedom go 60 and then 80. So you always want to be more conservative when you're doing this. So we're going to use the more conservative degrees of freedom equals 60. So using the more conservative, from Table B, we have to find our T star. So basically you go back to Table B, you're going to use 60, and you're going to go to the 95% because it asks you to do a 95% confidence interval. So you basically just find the place where they meet up. So where does 60 meet up with the 95% column? And that would be at 2. So that means that your T star is going to be 2.000 because you're using the 95%. So basically, the 95% confidence interval is this: B plus or minus T star times the standard error of the slope, which in this case would be 0.005724. That came from up here. So if I were writing this regression line, it would look like negative 0.03761 plus 0.005724x. So basically, what was the slope? That's the slope. That's B. So plus or minus. T star was 2 times the standard error of B, which we found was 0.002018. So what that means is you're going to do two separate ones, two separate equations because of that plus or minus. So you're going to have 0.005724 plus 2 times 0.002018. Whenever you do that, you would get 0.006128 if you do that on a calculator. You're also going to do 0.005724 minus 2 times 0.002018. And whenever you do that, you get 0.005328. All right, so if you remember back whenever we talked about confidence intervals, this one would be your upper bound and this would be your lower bound. So then C asks you to interpret the interval from part B in context. So you would say we are 95% confident that the interval from 0.005328 to 0.006128, this is in seconds per centimeter, captures the slope of the true regression line. So then D asks us to explain the meaning of 95% confident in context. So for D, you would say if we repeated the experiment many, many times and use the method in part A to construct a confidence interval each time about 95% of the resulting intervals will capture the slope of the true regression. In Chapter 3, we examined data from a study that investigated why some people don't gain weight even though they overeat. Perhaps fidgeting and otherwise non-exercise activity, NEA, explains why some people may have spontaneously increased non-exercise activity when they feed more. Researchers deliberately overfed a random sample of 16 healthy young adults for 8 weeks. They measured fat gain in kilograms and change in frequency use in calories from the activity other than deliberate exercise, fidgeting, daily living, and the like for each subject. Here are the data. Minitab output from a least squares regression analysis for these data is shown below. The problem asks us to interpret a 90% confidence interval for the slope of the population regression line. So to begin, we have to check and make sure that our conditions are met, and so we're going to use a t-interval for the slope to estimate what the slope is. So remember that whenever we are wanting to check our conditions, we have to use liner. So we're going to start with, is it linear? So to see if it's linear, we're going to look at the regression in the scatter plot, and we're going to look at the residual. So when we look at the scatter plot, we see that the scatter plot, which is this, shows a clear line pattern. They've even drawn in the least squares regression line. We also have to look at the residual plot. So when we look at the residual plot, we can see that that is our residual equals 0 line, and we can see that all of our points are randomly scattered about that residual equals 0 line. So we would say the residual plot shows a random scatter about the residual equals 0 line. All right, the I in liner stands for independent. So basically, is one of the subjects going to affect the other? So we would say individual observations of fat gain should be independent if the study is carried out properly. Because researchers sample without replacement, there have to be at least 10 times 16, 16 being because they had 16 subjects of people in the population of interest. So 10 times 16 gives us 160. So we basically want to know, are there 160 healthy young adults in the population of interest? Of course there are. So this is okay. Next, we're going to look at the N, which stands for normal. So to tell whether or not it's normal, we're going to look at the histogram and see what's happening with that. So with the histogram, we can tell that it's roughly symmetric. It's skewed a little bit, but not too bad. So we would say that the histogram of the residuals is roughly symmetric. And is also single peaked. So there are no departures from normality. All right, the E is going to stand for equal variance. So we're going to look again at the residual plot. And on this one, it's kind of hard to tell from so few points whether the scatter of points around the residual equals 0 line is about the same at all of the x values. So we would just say it's hard to tell. If the scatter is the same at residual equals 0 line. Next, we move on to R, which stands for is it random? And so in the problem, it says that people were randomly selected to participate. So because all of these work out, then we are safe in doing inference for the regression. So we would say with no obvious violations of any condition we should be safe doing inference for regression. So even though with equal variance we were kind of like, we couldn't really say one way or the other, because there's no obvious violations of any of the other conditions, then we would say that we're probably safe to do inference. So because we feel like we're okay to do inference, we're going to have to use a t-distribution. So this would be like our do step. So to do the t-distribution, we'd have to use the degrees of freedom of n minus 2. And because we had 16 subjects, that makes our degrees of freedom 14. If we go back to our table B, we would be looking for degrees of freedom at 14. It asks us to do a 90% confidence interval. So we're going to basically find where 14 and 90% match up, which would be at 1.761. So that makes our T star 1.761. So to do the 90% confidence interval, we would do B plus or minus T star times the standard error of B. So our B is our slope from our least squares regression line, which we can get from up here in the mini-tab output. And so remember that that would be y hat equals 3.5051 minus 0.003415x. Remember that this represents our A and this represents our B. So that makes our B negative 0.00344415. So that is going to look like in our formula here, negative 0.00344415 plus or minus 1.761 times our standard error of B. Our standard error of B would be 0.0007414. So when we plug that in, this is what we would be looking at. That plus or minus means that we have to split it up so that we have negative 0.00344415 plus 1.761 times 0.0007414. Whenever you work that out, you would get negative 0.002136. You would also do negative 0.0034415 minus 1.761 times 0.0007414. And whenever you do that, you would get negative 0.004747. So this would be your upper bound, this would be your lower bound, which makes your interval negative 0.004747, negative 0.002136. And so our conclude for that is we would say we are 90% confident that the interval from negative 0.00474 to negative 0.002136 kilograms captures the actual slope of the population regression line relating NEA change to fat gain for healthy young adults. Check your understanding. In Chapter 3, we examine the data on body weights and backpack weights for a group of 8 randomly selected 9th grade students at the Webb schools. Some mini-tab output from a least squares regression analysis for these data is shown. Number 1 asks us what conditions must be met for regression inference to be appropriate. So for number 1, we would need to first make sure that our liner conditions were met. So the first would be, is it linear? So to find out whether or not it was linear, we would look at the scatter plot. We would also need to know, is it independent? We'd also need to know, are the residuals approximately normally distributed? We would need to know that the residuals show roughly equal scatter for all the x values. And we would need to know if the observations were produced from random sampling or randomized experiment. 2 says, with such a small sample size, it is difficult to check several of the conditions for regression inference. Assume that the conditions are met and construct and interpret a 95% confidence interval for the slope of the population regression line. So we're going to assume that we've already gone through all of these and that everything was okay. So then we're going to just need to construct and interpret a 95% confidence interval for the slope of the population regression line. I would suggest starting by creating our least squares regression line. So that would look like y hat equals 16.265 plus 0.09080 x. So that means that this is A, this is B. It's also important that you have your standard error of B, which in this case would be 0.02831. So you'd need to know how many degrees of freedom you were going to use. So we know that to find degrees of freedom for this, it's going to be n minus 2. We have 1, 2, 3, 4, 5, 6, 7, 8. So n is 8. 8 minus 2, we're using 6 degrees of freedom. So we're going to go back to our table B. We're going to use 6 degrees of freedom, and it asks us to do a 95% confidence interval. So we're going to find 95%, and where does it match up with 6? And that is 2.447. So that means our T star is going to be 2.447. So then we're going to have to use our formula B plus or minus T star times our standard error of B, which in this case would be 0.09080 plus or minus 2.477, or 2.447, excuse me, times 0.02831. So whenever you do that, what that really means is 0.09080 plus 2.447 times 0.02831, which that gives you 0.16007. You'd also need to do 0.09080 minus 2.447 times 0.02831, and that would give you 0.02153. So then that makes your interval 0.02153 to 0.16007. And then it also asks us to interpret that. So we would say we are 95% confident that the interval from 0.02153 to 0.16007 captures the slope it's probably best to say actually the true slope of the population regression line relating pack weights, which we call our Y, to body weight, which we call our X, among ninth grade students at the Webb schools. The t-test for the slope of the population regression line. Suppose that the conditions for inference are met. To test the hypothesis H0, which says that beta, or the slope, is equal to the hypothesized value, compute the test statistic t equals slope minus slope naught of the standard error of the slope. To find the p-value by calculating the probability of getting a t statistic this large or larger in the direction specified by the alternative hypothesis, use the t distribution with degrees of freedom equal to n minus 2. So this is an example of when our alternative hypothesis says that the slope is greater than the hypothesized value. So notice that it's everything shaded to the right of the t statistic. This is the alternative hypothesis when the slope is less than the hypothesized value, everything to the left. And this is the alternative hypothesis when the slope is not equal to the hypothesized value. So this would be, these two would be one-sided, this would be two-sided. All right, so an example for significance tests for slope. Infants who cry easily may be more easily stimulated than others. This may be a sign of higher IQ. Child development researchers explored the relationship between the crying of infants 4 to 10 days old and their later IQ test scores. A snap of a rubber band on the sole of the foot caused the infants to cry. The researchers recorded the crying and measured its intensity by the number of peaks in the most active 20 seconds. They later measured the child's IQ at age 3 years using the Stanford-Binet IQ test. The table below contains data from a random sample of 38 infants. A says, here's the scatter plot of the data with the least squares line added. Describe what this graph tells you about the relationship between the two variables. So if you're looking at the scatter plot for the data, you can see that it's linear. You can see that because it's not as clustered together, the points aren't as clustered together as we have seen, that this is maybe a weak association, but it's still linear. So we would say there is a moderately weak positive linear relationship between crying counts and IQ. Scores. We can also say with no extreme outliers or potentially influential observations. So basically, to interpret that, we would say it appears that children who cry more vigorously tend to have higher IQs. So remember we talked about positive relationships when we talked about Unit 3 and how positive meant when one went up, the other went up. So for example, if the crying counts go up, the IQ goes up. All right. B says, what is the equation for the least squares regression line for predicting IQ at age 3 from the number of crying peaks, crying count? Define any variables you use. So we can get that from the mini tab output that was also provided to us in the problem. So we can see that our equation would be y hat equals 91.268 plus 1.4929 x. And then it asks us to define any variables that you use. So we would say x equals the cry count and y hat is the predicted IQ score. C says interpret the slope and the y-intercept of the regression line in context. So the y-intercept would be the 91.268. And the slope would be the 1.4929. So if we think about 1.429, 1.9, 1.429 actually 1.9 0.29. And we turn that into a fraction. And it may be better to use something like let's do 1.5. If we turn that into a fraction, we would get 3/2. So basically what that means is, keep in mind that whenever you were doing, when the scatter plot was created, the researchers recorded the crying and measured its intensity by the number of peaks in the most active 20 seconds. So what this means that for each additional crying peak in the most active 20 seconds, the regression line predicts an increase of about 1.5 IQ points. And this was for B. All right, for A, or the y-intercept, you would say the model predicts that an infant who doesn't cry when flicked with a rubber band will have a later IQ score of 91. D says, do these data provide convincing evidence that there is a positive linear relationship between crying counts and IQ in the population of infants? Carry out an appropriate test to help answer this question. All right, so we will want to perform a test of the null hypothesis. This says that the slope is equal to 0, and an alternative hypothesis which says that the slope is greater than 0. And we're using beta equals the slope, which is B. And so it's also important that you kind of word that here to say where beta is the true slope of the population regression line relating crying count to IQ scores. So because no significance level was given, we're going to use alpha equals 0.05. like we know to do from an earlier unit. So now we're going to have to do a t-test for the slope. So we're going to need to check our conditions. So remember, when we check our conditions, we're doing linear. So if we go back to the scatter plot that was given to us, we talked about the scatter plot a little bit already. We said the scatter plot suggests a moderately weak positive linear relationship between crying peaks and IQ. We can also tell that the residual plot would show a random scattering of points about the residual y equals 0. If we look at the residual plot here. So we'll say that linear is good. Next, we're going to have to worry about independent. So we would say later IQ scores of individual infants should be independent due to sampling without replacement. We would have to make sure that there were at least 380 infants in the population from which these children were selected. And so we got 380 by saying, using the 10% condition, so 10 times 38. We use 38 because it tells us that we had a random sample of 38 infants. So that would mean that there would need to be 380 infants in the population from which the children were selected. So that's true. Then we would look at normal. So we go up. We can see this talks about z-scores, so this has to do with normality. So for normal, we would say the normal probability plot of the residual slope shows a slight curvature, which you can see if you go back up and look at this. It's sort of starting to do this kind of thing, which suggests that the response may not be normally distributed about the line at each x value. With such a large sample size, n equals 38, however, the t procedures are robust against departures against or from normality. So for that one, even though it doesn't look like it's going to be quite normal because it does start to have that slight curve, we can say that because there is such a large number that we're looking at, that we're not really terribly worried about it. And then we will look at equal variation or equal variance. So to do that, we would look back at the residual plot, and we would see if our residual plot showed that we had the same variance from the residual equals 0 line. So the residual plot shows a fairly equal amount of scatter around the horizontal line at 0 for all the x values. So for that one, we're good. And the last one is random. And so it states in the problem that it's random, so we're good on that as well. So with no obvious violations of the conditions, we proceed to inference. So now we're going to do the do step. I'm going to have to move over here because I don't have enough room. All right, for the do step, we're going to have to figure out what our t-statistic and what our p-values are going to be from Minitab. So to get our t-statistic, we would be doing b minus beta naught over the standard error of b. So that would be 1.4929, which came from here, minus 0, because we're going to assume that the slope is 0 at 0, over the standard error of the slope, which would be 0.4870, And when we do that, we get 3.07. Now, we calculated that by hand, but the mini-tab also gives us that value right here. So if you need to find the t-statistic or the test statistic and you're given mini-tab, you'll always look in the t column in the row that has to do with what your slope is. You'd also need to get your p-value. The good thing about having your mini-tab output is that it gives you your p-value. So to get your p-value, if you're dealing with slope, you're going to look in the p column and you're going to look across in the same row as you were dealing with your slope. So this would be your p-value. But this is your p-value if this were a two-sided test. Yours is not a two-sided test because you were looking at when beta was greater than 0, which just means it's a one-sided test. So basically, if this is for a two-sided test, you would take this value and divide it by 2, and that would give you your value for a one-sided test. So your p-value would be 0.002. The last thing you have to do is conclude. So just kind of wrap everything up. So you would say the p-value 0.002 is less than our significance level alpha equals 0.05. So we have enough evidence to reject the null hypothesis and conclude that there is a positive linear relationship between intensity of crying and later IQ scores. The previous Check Your Understanding describes some results from a study of body weights and backpack weights. Again, here is the mini-tab output for the least squares regression analysis for these data. One says, do these data provide convincing evidence of a linear relationship between pack weight and body weight in the population of 9th grade students at the school? Carry out a test at the alpha equals 0.05 significance level. Assume that the conditions for regression inference are met. For number 1, we need to start out with state. So let's state what we're actually doing. So we want to perform a test of the null hypothesis where beta equals 0 versus the alternative hypothesis where beta does not equal 0. where beta is the true slope of the population regression line relating body weight to backpack weight. And so we will use the alpha equals 0.05 significance level. All right, then we need to plan. So for the plan, we'll say if the conditions are met, which it says in the problem that they are, we will do a t-test for the slope beta so because we already said that the conditions are met, we are assuming that everything's good to go. Then we're going to move on to do. So according to the output, which is up here, we can get the t and the p from that. The test statistic is t equals 3.21. Remember, you're going to go in the row that has to do with what the slope is. So this is the A, this is the B, so that's the slope. We're looking for the t in the t column for slope. So the t statistic is 3.21 and the p-value is 0.018. Same thing here. So t is going to come from the t column, p is going to come from the p column, but you got to use the row that has to do with slope. And this was using degrees of freedom equal to 6. So they were able to calculate the t and the p by using degrees of freedom equal to n minus 2, where n was 8, so we did 8 minus 2, which gave them 6. So they calculated these numbers in the program and figured out the t and the p by using 6 as the degrees of freedom. And so then the last is to conclude. So for that, we would say, looking at the p-value and comparing it to the significance level, we would say since the p-value 0.018 is less than the significance level 0.05, we reject the null hypothesis and conclude that there is convincing evidence of a linear relationship between body weight and pack weight. Number 2 said, would a 99% confidence interval for the slope beta of the population regression line include 0? Justify your answer. You do not need to do any calculations to answer this question. So basically, for this one, the answer would be yes. And the reason that it would be yes is we would say the 99% confidence interval would contain 0 because the p-value, which is here, 0.018, is for a two-sided test. And because that p-value is greater than 0.01, then it would include 0. So the good news is you can do this stuff on the calculator as well. So to do this, we're going to go ahead and put everything into the calculator using, for the x values, L1, the NEA change. And then for L2, that would be the fat gain, which would be your Y's. So then from there, you would hit stats, go over to tests, and you're going to do the Lin Reg t-test, which is going to be F. So you can do alpha, and then the cosine button, and that would take you there. So hit enter. So then you can see we're going to use X as L1, Y as L2, keep the frequency. This time we want to change this to not equal to. This stands for beta and alpha. So then you'll just hit calculate. And that gives you the T, gives you a P, gives you your A and B so that you can write your regression line. And so then you've got your mini-tab regression output here, and you can basically match it up, make sure that everything works. So for P, the p-value that the calculator calculated was 3.8095432 or 31 e to the negative 4, which just means move that decimal back 4 places. They on the mini tab just said it was 0 because it essentially is so small. Everything else though pretty much matches up exactly the way that it is in the mini tab. All right. From there, if you wanted to calculate an interval, then you would go to Stat, go over to Tests, and you would do a ln reg t interval, which is G. So you'd have X as your L1, Y as your L2, frequency would stay at 1. If we wanted to do a 95% confidence interval, we would do 0.95 and then calculate. And whenever you do that, you've got your lower bound, your upper bound. They give you your degrees of freedom, give you your A and your B, pretty much everything else that you need from there.